So this is our final example for this set of videos. We've done a lot of working with regions of integration, and now we're going to apply that to a new problem where we're trying to find the volume of a solid between the planes x plus y plus z equals 2 and the plane x plus y plus 2z, that's a z, equals 2. The difference between this problem and previous problems is that before we've always been given our f of xy, which was the top of our loaf, and we've always been given some region that was the bottom of our loaf. And in this case, those things aren't as explicit for us. So we're going to have to come up with our region of integration. Let's start by sketching a picture of what these planes look like. I'm going to take a look. Oh, it should be between these, but we have to be in the first octant, meaning that there's an infinite number of volume, like these planes intersect with one another, but you would think that there would be an infinite amount of volume between the two of them. Regardless, let's go ahead and draw the picture. So I'm going to do my blue plane is going to be this plane. So the blue plane, we know that x plus y plus z equals 2. The easiest way for me to start drawing this plane is by plotting some points. And I see that when two of the variables are equal to 0, the other variable has to be equal to 2. So that gives me my intercepts. 0, 0, 2, 0, 2, 0, and 2, 0, 0. So it means that this plane is cutting into, the plane extends outwards in all directions, but where it slices into the x, y's, and z's axes are what is labeled here. X. Let's take a look at the second plane. The second plane I'm going to draw in green. So the second plane is going to be very similar, only let's plug in some zeros. So when both y and z are equal to 0, x is still equal to 2. So we have the same point in common. When x and z are equal to 0, y is equal to 2. So this point is also in common. Means that they share this line in common. However, when x and y are both equal to 0, my z value is only up at 1, which means that this plane is going to be sort of a shorter, squattier plane, right? That's where that plane lies. And we're trying to find the volume of the solid between the planes. So in this case, the volume of this solid, it's going to be the lower tilty green plane and the upper tilty blue plane are going to be the two different planes. So the trick here is that the region of integration isn't explicitly given to us, and we have to find out what is the region of integration. Meaning, if I were to take a bird's eye view and look down onto this solid, what would the shadow of this be in the xy plane? So in general, the region of integration is the shadow that the volume makes in the xy plane. So in this case, we see that if we were to project this down into the xy plane, we only want the region, the intersection of these regions in this front half. Means the shadow that it makes is going to be this triangular base. So I need to be able to describe this triangular base as a region. And the function itself is going to be the top plane minus the bottom plane. But let's concern ourselves first with the region. So the region, if I were to draw this region, the bird's eye view in the xy plane, here's my x, here's my y. And I know that we have a couple of points on here. Here's the point where x equals 2, here's the point where y equals 2, and we want this triangular region. So if I were to describe this triangular region, I think the easiest way to describe this region is to think of it as a type 1 region. I need to find an equation for this line. This is the line y equals 2 minus x. I know that because my intercept is where y equals 2, and I have a slope of -1. So that means that my y values are going from down where y equals 0 up till this line, which is the line 2 minus x. And I know that my x values in this case are going from 0 to 2. It is tempting, and you will be tempted, to always write that my x values are going from 0 to 2 and my y values are going from 0 to 2. Because it's true that that's where those intercepts are. But if I did have my x values go all the way to 2 and my y values go all the way to 2, then I would be tracing out this entire rectangular region. And we don't want that much region. We want the region to be just a little triangle. So we need to make sure that we bump in and make sure our y's don't go all the way to 2 all the way across. Because if they did, we would end up with a rectangle. That's my loud voice caution, because that's something that's very easy to do, and we don't want to do that. So now we have the bounds of integration. We need one final step. We need to come up with our function. And in this case, our function, we're going to solve for our z values. And we see that in this case, using our blue function, we see that z is equal to 2 minus x minus y. That's one of our z functions. And this other z function is given by 1 minus 1/2 x minus 1/2 y. And we want to know the upper plane function minus the lower plane function. And we can do this a number of different ways. I'm going to set it up as two separate integrals. So with all of this work, I'm going to erase these pieces, keep that up. We now know that I want to take the integral. My x values in this case, as we found over here, are going to go from 0 to 2. My y values in this case are going to go from 0 to 2 minus x. And the function that I'm using, I could combine these functions if I wanted to, but I'm just going to find the volume under the big plane and then subtract out the volume under the small plane. If I do that, I get 2 minus x minus y dy dx. This is the volume under the big plane on this triangular region. And now I'm going to subtract out the volume of the littler plane, 1 minus 1/2 x minus 1/2 y, on this triangular region. And the triangular region, my x values are going from 0 to 2, and my y values are going from 0 to 2 minus x. And if I were to compute all of these pieces, it would give me my final integral value. Notice that if I wanted to, because the region of integration is the same, I could combine all of this into one single integral. And maybe it is easier for me to combine it. So I'm going to combine this into one single integral, dy dx, by taking the interior and subtracting each of the pieces. I could compute this integral and then this integral and subtract them, or I could think of subtracting it and then integrating. If I do subtract and then integrate, I'm thinking of getting 2 minus 1, which is giving me 1. Negative x minus 1/2 is going to be adding a half to a negative x, so that's minus 1/2 x. Negative y minus 1/2 y is negative y plus a half of a y becomes just minus 1/2 y dy dx. X equals 0 to 2, y equals 0 to 2 minus x. So now I just have to integrate. When I integrate with respect to y, these two terms are just constants, and so they're just going to disappear. They don't just disappear. You can tell I'm getting a little tired. So when I integrate with respect to y, I treat these as constants, and so I'm going to add a y term to each of those. So it turns out that this ends up being keeping the integral on the outside with respect to x. I integrate this inside with respect to y, and I get y minus 1/2 xy minus 1/2. Integrating this y, I get 1/2 y squared. I need to evaluate this from y equals 0 to y equals 2 minus x. So I'm going to plug in, notice when y equals 0, all these terms become 0. So I'm going to plug in 2 minus x, and I get the integral as x equals 0 to 1. Plugging in 2 minus x everywhere I see a y, I get 2 minus x minus 1/2 of x times 2 minus x minus 1/4 2 minus x all squared dx. I'm going to erase a whole bunch of this so that I have more room for my integration. So I'm left with an integral where x equals 0 to 1 of 2 minus x minus 1/2 times 2x minus x squared minus 1/4 times 2 minus x quantity squared dx. In order to integrate this, I'm going to simplify it a little more. Again, this is just algebra. My x goes from 0 to 1. I have 2 minus x. Minus 1/2 times 2x becomes minus x. And this becomes plus 1/2 x squared. Now, I'm going to do a little bit of scratch work and do this 2 minus x times 2 minus x times 1/4. I end up with 2 times 2, which is 4, negative, well, I'll just do this step by step. Minus 1/4 times 4 minus 4x plus x squared dx. I have one more step where maybe I have 2 more steps where I'm going to simplify a little more. I get 2 minus 2x plus 1/2 x squared minus 1/4 times 4 becomes minus 1. Minus 1/4 times negative 4x becomes plus x minus 1/4 x squared dx. I can combine some of these terms. Negative 2x plus x becomes negative 1x. I'm just going to erase. And then 2 minus 1 becomes 1. I'm also just going to erase. So I'm left with the integral from x equals 0 to 1 of 1 minus x plus 1/2 x squared minus 1/4 x squared dx. Oh, 1/2 minus 1/4, I should combine those because that just becomes positive 1/4 dx. Let's go ahead and integrate, and I get x minus 1/2 x squared plus 1/12 x to the third, evaluated from x equals 0 to 1. Plugging in 0 here gives me a 0, but plugging in 1 gives me 1 minus 1/2 plus 1/12, which is 1/2 plus 1/12, which is equal to, how many is that? 6/12 plus 1 more 12 becomes 7/12. And we're done. Thanks so much.